Hello, my name is Brendan Hertel, and today I will be presenting on the paper Learning from Successful and Failed Demonstrations via Optimization, co-authored by Dr. Ahmadzadeh and myself. Users need to be able to teach robots new skills effortlessly and robustly. One of the most prominent methods of teaching new skills is through learning from demonstration, or LFD. In LFD, a user demonstrates a skill to a robot through methods such as kinesthetic teaching, shown here. The robot is able to record the demonstration, interpret it through some LFD representation, and then reproduce the skill under novel constraints. Most LFD methods rely on the assumption that demonstrations are either optimal or near optimal. Ideally, the user is showing the robot what to imitate with a demonstration that successfully performs the skill. Few methods incorporate data from suboptimal demonstrations, which account for what not to imitate. These suboptimal demonstrations could be complete failures at performing the desired skill. We propose that the data from these failed demonstrations can be incorporated into the learned skill model in order to better reproduce the skill. For example, here 4 demonstrations of a 2-dimensional reaching task are shown. These demonstrations cover a large task base, and an LFD representation should be able to reproduce the task successfully. However, if the environment changes and a box is added into the scene, this could cause some of the demonstrations to fail. The position of the box itself is not encoded into the LFD representation, only the demonstrations and their labels as failure or success. Using only information from successful demonstrations, the reproduction arrives close to a mean of the 2 demonstrations, which collides with the box and would not succeed. However, by incorporating data from the failed demonstrations, we can use that information to find a reproduction which avoids areas of failure. To achieve this, we propose trajectory learning from failed and successful demonstrations, or TLFSD. Provided with a set of successful and/or failed demonstrations, TLFSD encodes each labeled set into a skill model, uses those skill models to construct a cost function, and optimizes this cost function to find an optimal reproduction, which converges to successful demonstrations and diverges from failed ones. Additionally, the proposed reproduction given by this optimization can be labeled and reincorporated into the skill model to further refine the learned model. In this example, we show 2 reproductions. The first reproduction uses TLFSD with only data from the successful demonstrations. As it can be seen, this reproduction collides with the box and is unsuccessful. Next, we provide information from the failed demonstrations as well, and show how this reproduction avoids the obstacle by avoiding the failed demonstrations, thereby successfully reproducing the skill. There have been few previous works which have explored the use of failed demonstrations and are relevant to our work here. The first would be Do Not As I Do, Learning from Failed Demonstrations. This method uses only failed demonstrations and iteratively explores around the task space in order to find success. While this method does work, it is not able to incorporate successful demonstrations, which provide important information on how to perform a skill. Additionally, it assumes that failed demonstrations are close attempts at completing the intended skill, which may not always be the case. Our approach, on the other hand, does not rely on this assumption. Alternatively, another approach proposed uses inverse reinforcement learning techniques known as inverse reinforcement learning from failure. This relies on the inverse reinforcement learning process, which can be slow and challenging for some users, as it relies on user-defined features in order to find a reproduction. TLFSD does not use this process or require the user to define any features. Here we show a flowchart overview of the TLFSD process. The process starts with the human user providing labeled demonstrations. Our approach can incorporate sets of failed and/or successful demonstrations. We will show that one of these sets can be empty. Once these demonstrations are provided, they are each separately encoded into a skill model. Any statistical method which provides means and covariances can be used, but in our applications, we use a combination of Gaussian mixture models and Gaussian mixture regression, known as GMM-GMR. Once these means and covariances have been found, they can be used to construct a cost function. The cost function has two terms, a quadratic cost function and a regularization term. This quadratic cost function penalizes divergence from the success and rewards divergence from failure. We start with a general cost function shown here. This general formulation penalizes the square distance between some mean m and the reproduction x, weighted according to the inverse of the covariance sigma. This formulation penalizes divergence, so we use a positive weight when calculating divergence from success and a negative weight when calculating divergence from failure. However, we weight the failure term according to a dissimilarity vector between the two means, known as WSIM. This term is used because areas of high similarity between failure and success are likely not the reason for failure, and divergence from these areas should not be highly rewarded. Next, we use a regularization term in the optimization, which provides features such as smoothness to the reproduction. This regularization term models the spring energy between points along the reproduction. Minimizing spring energy reduces jaggedness in the reproduction, leading to smooth reproductions. The lambda parameter represents the spring constant and must be tuned. By combining these two terms, we can apply constraints and minimize to find an optimal reproduction. However, for use with unconstrained optimization algorithms, we transform the constraints into a third quadratic penalty term. This term penalizes deviations from the constraints given according to the rho parameter, an arbitrarily small constant. We have solved this optimization problem with solvers such as CMAES, differential evolution, and BFGS. Finally, once an optimal reproduction is found, it can be reincorporated into the skill model to provide more information for future reproductions. A user can label the reproduction as either successful or failed, which is then encoded into the learned skill model. This is especially useful in the case of failed reproductions, which can be reincorporated and learned until the model finds a successful reproduction. In this first experiment, we show the uses of TLFSD with different inputs on a 2D reaching task. Here, 2 successful and 2 failed demonstrations are given. We first perform TLFSD given only the successful demonstrations. This reproduction conforms to the given constraints and follows the successful mean, but does not necessarily avoid failure. Next, we use TLFSD given only the failed demonstrations. This reproduction somewhat avoids the failed demonstrations while adhering to the constraints, but does not strongly follow the successful demonstrations. Finally, we find a reproduction with information from both failed and successful demonstrations. This reproduction strongly avoids failure and adheres more to successful demonstrations while conforming to the given constraints. This experiment shows how our approach performs given successful demonstrations, failed demonstrations, and both failed and successful demonstrations. The next experiment compares TLFSD with a skill refinement method on a 2D pushing task. The representation we compare against is GMM-GMR with weighted expectation maximization. This method assumes newer demonstrations are more optimal and refined than older demonstrations, and therefore weights newer demonstrations more strongly than older demonstrations, pulling the mean closer to newer demonstrations. We provide 3 failed demonstrations to begin. These failed demonstrations follow a trajectory towards pushing the drawer closed, but lift above the target before reaching the drawer. We iteratively add successful demonstrations. After a single successful demonstration, our approach is able to successfully reproduce the task by following these successful demonstrations and avoiding failure. The compared method, GMM-GMR with weighted expectation maximization, requires 2 additional successful demonstrations before the reproduction is sufficiently refined. This experiment shows the advantages of TLFSD in learning skill refinement scenarios. Next, we show the performance of TLFSD compared to conventional single demonstration LFD representations in a writing task. 1 successful and 1 failed demonstration are provided. We compare against dynamic movement primitives, or DMPs, as well as Laplacian trajectory editing, or LTE. These representations are only given knowledge of the successful demonstration, as they do not incorporate failed demonstrations. Here we show 3 reproductions. We compared using 3 different metrics. 2 metrics measured spatial dissimilarity, one with temporal dependence and one without. The final metric compared dissimilarity in curvature space. Spatially, it was found that TLFSD provides the most similar reproduction, as it quickly converges to the successful demonstration. However, in curvature space, TLFSD was found to be the most dissimilar reproduction. As can be seen, LTE and DMP maintain the shape of the successful demonstration well, but TLFSD does not. In a writing task, curvature can be very important in determining the success of a reproduction, which TLFSD does not account for. We will later present an extension to TLFSD, which can incorporate different coordinate spaces in order to capture more features of demonstrations. This experiment shows the iterative learning process of TLFSD in a 2D reaching task. Here, there is an unknown obstacle placed between the initial and final points. A single demonstration is given which collides with the obstacle and labeled as failed. TLFSD proposes a reproduction which is not successful. A human teacher labels this reproduction as failed, which is then incorporated into the model, and a new reproduction is proposed. This too collides with the obstacle and is labeled as failed. Finally, after 3 iterations, the proposed reproduction avoids the obstacle and is considered successful. This shows how reincorporating failed reproductions can be used to iterate towards a successful reproduction. Next, we use TLFSD with a real-world Universal Robots UR5E manipulator arm. Demonstrations are provided for a reaching task through kinesthetic teaching. 4 TLFSD reproductions were found, which all successfully complete the task. Then, an obstacle is introduced to the environment, which causes some demonstrations to fail. These are labeled as failed by a human user. The TLFSD reproductions are able to adapt and avoid the obstacle, successfully completing the task. Finally, we propose an extension for TLFSD to incorporate more coordinate spaces in order to capture more features of demonstrations. We use a 2D writing task with 3 failed and 3 successful demonstrations. Using only the single coordinate TLFSD, a failure is avoided, but the shape of successful demonstrations is not preserved. However, by introducing multiple coordinate spaces, the shape of the successful demonstrations is maintained, which leads to a more successful reproduction in tasks such as writing. As presented here, our approach performs well at incorporating information from successful and failed demonstrations. There are possibilities for this to be extended and explored further, particularly in the learning process. One possibility is the incorporation of skill refinement techniques, which would likely perform better than the trial and error iterative solution used currently. Additionally, learning could likely be improved by encoding semantics, which could then be used to learn why demonstrations fail. I would like to thank you again. My name is Brendan Hertel, and this presentation has been for learning from successful and failed demonstrations via optimization.